Hi, this is Chris West for House Calls Vermont. It is part 3 of my interview with Jacob Deva Racusin from New Frameworks. We're going to be talking, welcome Jacob once again. We're going to be, an odd thing happened. I think it was something like 4 or 5 years ago at this point. Give me just a second. My tape fell.
Aha.
Dude, you can't see behind the curtain.
Oh, adhesive failure.
Maybe I'll change this to not be on that particular. Let's go to the techniques page. There we go. Something like that. I'll just leave that up in the background. More New Framework stuff. Okay.
Love it.
Good. Let me start that again.
Sure thing.
All right, we'll go. Hi, this is Chris West from House Calls Vermont, and this is part 3 of my in-depth interview with Jacob Deva Racusin from New Frameworks. Welcome back, Jacob.
Hey, Chris.
Hey, so we started talking about the culture of New Frameworks. We then went on and spoke a little bit about embodied energy and equivalent carbon dioxide, cradle to gate, and tools, and how we're trying to push these things on a policy level. But a number of years ago, you and I independently took this class by Robert Bean called Integrated Heating Design, which was given through Heatspring, which I highly recommend. It's a great platform if you're interested in some interesting courses, and a lot of good building science courses on there. But this was a course specifically about using low temperature and sometimes extremely low temperature heating systems. And one of the things that was a hard one for me to wrap my head around during the course was the idea of, oops, I'm just going to leave the wires. What is the idea of exergy destruction? So when you have a boiler, and that boiler is running on a regular, say, slant fin baseboard radiator, you're putting 190 degree temperature water into the system, you're getting 170 degree temperature water out after it's heated things, and then that boiler is heating that 20 degrees up and again. And exergy is what we used to call, because it's a term that I was not taught in engineering school, used to be called useful energy. It's the energy you can actually use for the purpose it was created for. And what Robert Bean was pointing out, and Robert Bean is an incredible, interesting person in and of himself, and one of the co-authors of the ASHRAE 55 standard. He was saying that the higher the temperatures are, the more exergy destruction you're suffering from. The harder it is to get that useful heat or energy to the place that you want to use it. So the lower we can get those temperatures, the less we're destroying or we're creating energy that we can't use for its purpose. And we all know this. We've all been in a boiler room where the boiler room is 15 degrees hotter than the rest of the house. Well, that 15 degrees is the energy that system is not getting to the radiator, right? So, and efficiencies, right? If we're gonna burn a material to turn that material into heat and have that heat transfer, what's the efficiency of the burning of the heat exchanger in the burner? All of those things lead to the general destruction of useful energy that we're spending resources to mine or to make the fuel, or to bring in the fuel from some other place. And part of trying to reduce our use of fuels is to look at that side. So when we have a heating system is a thing that makes the heat, and then there's the thing that distributes the heat. And the thing that makes the heat is the boiler, and the thing that distributes the heat is your distribution system. If it's forced hot air, those are your forced hot air ducts. If it's a radiant hydronic system, like a slant fin baseboard radiator, then that is the tube with the fins on it. And those two things are separable, and the efficiencies of those two things are linked to each other, but they're not specifically the efficiency of the radiator system is not the same as the efficiency of the boiler, say, for instance. And in this class, we were taught that if you can get your temperatures down below 130 degrees, that you are now dealing with a temperature that a condensing boiler can actually get its higher efficiencies because it's able to reuse some of the fuel, some of the energy in that fuel, and get from the upper 80s up into the upper 90s. You can never get above 100% efficiency with a combustion process because you have a finite amount of energy in each molecule, and that can only give up so much energy. When we're talking about heat pumps, it's not really that heat pumps are more than 100% efficient. It's just that it's getting the heat from outside of the system, and that is how we then can say that a heat pump is more than 100% efficient. And we can get into the details about that at some point in a educational video. But just for a point for this discussion, what we're looking at is super low temperature radiator systems. Radiant floor is the one that most people know about. There are also radiant pillars, also called chillers, and there's radiant walls and radiant ceilings. And specifically, what Robert Bean was pushing was the concept of radiant ceilings. And Jacob is the first person that I know who has actually put together and installed a radiant ceiling system, which is what I wanted to speak to him about during this segment. So, Jacob, welcome back. Sorry for the long exposition to get started, but
that was great.
Set the stage.
Yeah, totally.
So, tell me about the is it just one project at this point that you've used that system with, or have you used that system in more than one project?
For the radiant distribution, yeah, just one project we did is new construction. Although I will say we did a weatherization job 6 some odd years ago, sometime in the middle of the 2010s, that had the complaint that we heard was that the heating system is really uneven, and in many cases just not sufficient. The homeowner couldn't identify any baseboards, couldn't identify any distribution they were building. We went up into the attic to prepare to do some just like inspection around air sealing. You're always digging around the attic floor to see where the holes are in the ceiling.
The distribution pipes?
Huge network of copper radiant ceiling distribution pipes with like this much insulation over the top, if any, and these massive holes where things are kind of like popping back down. And so we kind of made sure the system was good to go and, pressure tested and leak checked and all that jazz. Made sure its operation was sound. Then air sealed and insulated the hell out of it. And then amazing. Her house is like, she loves it. Her heating system is just like absolutely fantastic.
So she was literally heating her attic.
More of it was going up than going down, which sure, that makes sense. So it's my second radiant ceiling project, but the first one that I actually did all the hydronic design, and we did it as a full design build in house. Yeah, and it's awesome.
So
it's so great.
Bring me through a little bit. So what I've been looking at is as a proponent of radiant ceilings. One of the things that we were taught by Robert in the class was that radiant floors are 60% radiant and 40% convective, right? There's a convective component to a radiant floor. You're heating up air, warm air rises, that pushes cold air, that cold air goes down, and you get these convective cycles, which there's nothing wrong with having a convective component to your heating system. It's just harder to regulate what's going on as soon as you start letting these convective pathways. We say that about wall cavities, right? We don't want voids in walls where moist air can circulate. There's another place we talk about convective loops. We talk about the stack effect. And how the stack effect affects how buildings operate, and that of course is a convective loop that's outside of the building, right? The air goes up and pushes out and then re-infiltrates at the bottom of the building, so that's a convective loop. But we try to keep convection down unless we're heating with convection, like forced hot air or heat pumps, because it's not as useful for transferring energy. Air is just much less dense as far as its ability to transfer energy than radiation. Radiation is much better. A surface that's radiating heat is better at creating and now I'm thinking in Dutch, a level type of heat,
Even,
right? Instead of a cool pocket here, a warm pocket there. When I'm doing my research to try to find products for radiant walls or radiant floors, I've been having to put stuff together myself, and you seem to have found a product that was kind of off the shelf. I want to hear a little more about this product, and you know, we're gonna get a bit technical here, people, so don't get worried. We're gonna talk about thickness. We're gonna talk about the diameters of pecs and all that type of stuff. So get ready, strap in. Tell me a little about the BTU per square foot output of the system that you ended up designing, and the products that you were able to find to do it, and how happy you were to work with them.
Yeah, absolutely. So we ended up, I guess the quick caveat I want to give in describing the system, so as I know folks are immediately going to try to start applying it to their own project. So all this is predilected on the high performance enclosure.
Right.
And so just to be
low
like super clear,
yeah,
exactly. Like that's how all this works. I'll say first and foremost, invest in your enclosure all the time, every time you unlock all of these mechanical solutions and these improved parameters around performance and impact and comfort when you're starting from a good quality enclosure. So just feel like I have to say that first.
Thank you for that. So, caveat is very important. When we go into a house and the first thing I'm doing an energy audit, and the first thing the client says is, "Oh, I heard heat pumps were good." And I'm like, yeah, but your house is 20 air changes per hour at 50 pascals. A heat pump's not going to help you reduce the load, and then these other systems really work well. Thank you for pointing that out. Yes.
Exactly. Yeah, and so we actually initially were looking at radiant floor, and we've done a number of hydronic floor systems. And I try to say actually hydronic floor rather than radiant floor for the thing because the reason you just brought up. It's actually not. Yeah, there's conductiveness, there's other things going on there too. So hydronic speaks of tubing in the floor. What we found in a bunch of these projects is that the whole idea of the hydronic floors being warm and the whole warm floor thing doesn't really play out for us because we're intentionally trying to keep those flue temperatures as low as possible for the sake of the performance and energy efficiency of the building. And also, from a control standpoint, when we only need these like little injections of heat in a low load building, if you have that floor warm enough that it is higher than the surface temperature of your feet by enough of a span that you can really feel that it's warm, then you're going to bake yourself out of your house. Yeah. And so we just haven't. It's been like a happy outcome. I consider it happy that. You don't have to have really warm floors. You just don't need that much heat in the building to be able to keep the building really even. So the forms don't feel cold; they just feel neutral. Yep. And so, that benefit isn't necessarily there from a radiant floor in a low load building.
And what Robert was teaching us is that studies have shown that there's a real low temperature upper limit to what's comfortable for people's feet. It's like 82 degrees is comfortable, and you get up to like 85, and people are like, my feet hurt. So there's also
you start getting sweaty. Yeah, totally, exactly. And you look at all the different factors of human comfort. There's like a dozen, maybe. There's about 7 that I can think of that I work with a lot. And asymmetry is one where heat's coming in different sides, and stratification is another. Like how warm is your head versus your feet? Like all these things really factor in.
Yeah, I call that the fire the fire pit thing. It's 25 degrees.
Yeah.
And outside, the front of you is really warm. The back of you is really cold.
When you rotate like a stick. Yeah, exactly. Yeah, or like the rocking chair for the wood stove, or the drafts are blowing behind you. Exactly. And so in this project, we're initially looking at radiant floors. There's a couple of reasons that we moved away from them. One, a diversity of flooring types made the hydronic design a little bit tricky in terms of allowable fluid temperatures over different flooring types and some of those transitions. Another was furniture placement, and it was highly variable as to how much furniture was going to go where and how much of the floor aperture is actually going to be visible to
Yeah,
us.
and that is
Which
so
means we
so
would have had,
dependent on the person, right? Because you could sell the house and they've changed their furniture
and will
patterns.
change.
Yeah, yeah,
So unless you're going to put tubing literally
yeah.
everywhere, and then like that's a solution that can get pretty expensive. In this case, that was going to definitely be a cost driver, partially because of the product that we're looking at and working with, and partially because that would have meant we had to insulate the entire floor below. And so now we're dramatically increasing, a whole bunch of insulation that otherwise wouldn't have necessarily needed to be in there between floors. And so, a bunch of those things were all sort of conspiring together. They're like, well, let's look at the ceilings. And that ended up being like a way more targeted use of area, more predictable in terms of furniture arrangement, surface material. We are able to take an entire floor diaphragm of insulation out of the work scope. And then we had the advantage of everything in the room can be seen radiantly by that ceiling.
Right.
It's all line of sight.
Right.
So all the belongings and surfaces in that room are up to whatever that radiant design temperature is. And so its effectiveness around creating this totally even, comfortable distribution of heat is really, really high.
And that
So what
that
we did in
also
our
plays back to what Robert was saying, is that radiant ceilings are 100% radiant. There's no convective component because there's nothing above it to heat. The air is already at its highest point in the room.
Exactly. And so what we did in our project, we had a couple different conditions. There was like a great room that has it's like 2 stories plus a bit. So we call it 20 some 25 feet maybe ish from the very peak down to the first floor. And so those ceilings are all radiant. And then we had 2 stories that have more flat ceiling, kind of standard 8-foot tall ceilings. Those had radiant. And then the basement level, as a cost reduction approach, we use like a baseboard wall panels. So not a convective baseboard slant fin style, like fin tube style, but more actual like radiant panel.
Was that like a low temperature European type?
Yep. Yeah, Meissen and Runtal are the 2 manufacturers that I'm aware of. In this case, we worked with Runtal. Meissen is another direct competitor, kind of a Ford Chevy thing is my impression. So the basement was satisfied with those. About half the basement is unfinished.
Wait a second, did you just indicate that Ford and Chevy are not comparable? Your metaphors sometimes bring me places. Anyway, go on.
2 closely competing brands within the marketplace.
Basically the same product, yes.
I don't need to piss off any Ford or Chevy owners in suggesting there might be equivalence between those brands. Nor Runtal or Meissen diehards that have.
And they're out there.
I don't know enough about that world to comment any further, other than they're both good options. Yeah. But so we used our system. So first of all, there needs to be a generous amount of insulation on the non-heating side of those panels, because radiation will go in any direction along a concentration gradient. So if you want it to go in one direction, you need to make sure that it's a lot easier for the energy to go that way than the other way, which means insulation. The general term I hear thrown around there is R19. What I try to dial that in a little more specifically and look at a 30-to-1 ratio, that for every inch of R that is between the tubing and the room, try to get about 30 times that on the other side. And again, that's just a matter of efficiency and making sure that the heat energy is going in the direction you want and isn't warming up a cavity.
Right.
If that's not necessary. Again, it's a usefulness of that energy and efficacy of how that energy is being delivered. And so the nice thing about ceilings, and we already have in that cathedral great room, like the insulation is already there. So there's nothing extra. Yeah. The second story going up by the ceiling, like it's already insulated.
It's that
we're already
first
there.
Floor ceiling, that's the interesting one.
Yep. So we added insulation in that part of the room. And what we did, because our building was so low load, even with, I think our design temperature for the fluid was 110 degree entering water temperature. So the tank is 110. We actually had the tank set to 103 all last winter, and this is in Charlotte, Vermont. And we had some pretty darn cold parts that winter, and 103 was fine.
Awesome.
So we're circulating 103 degree water as it's entering the system, and that's keeping the whole house up to temperature. And so even with those low temperatures, we did not need the entire surface area of the room to be tubed. That was way more surface area than was actually necessary. And so we had some routing of that tubing. Actually, I routed around the perimeter of the building to really make sure that the cold surfaces of the walls and windows were going to really make sure that those were going to most directly benefit. Yep. And we were able to target our insulation accordingly. We didn't have to insulate every single bay of that floor. We sort of really insulated over where the panels were. And that was really targeted and effective for us. Whereas with the floor, we really would have had to insulate the entire floor for all practical purposes, not knowing where that bed was going to be. And we lost, upwards of 50% of the floor area in any given room between closets, beds, dressers, and other, furniture that would have really impacted the delivery efficacy of the heating system. So we were able to cut we cut like 30% material out of the installation in area reduction by going to ceilings rather than floors. And so should I describe the system?
Yeah, please. That was my next question.
Yeah.
What is the actual system?
So we have these insulated cavities. That's sort of where we just left off. We used a product called Warm Board, WARMBOARD. That is essentially like an MDF or an OSB or an MDF. I can't exactly remember. I believe it's more MDF style board that's routed to receive 1/2-inch tubing. And it's sort of routed. They've got left and right turn ends, center turn ends, and then common middles. So you have a kit of parts that you then, they do the design to your layout to make sure that you have the right sets of parts that all map together. And it's routed to receive your tubing on, I think it's 4-inch spacing. So you have some, it's either 4 or 6-inch. So you have some play in what you want your tubing spacing to be, depending on your design needs. And then all of that is covered with an aluminum, it's like a heat spreading
plate
covering. Yeah. Spreading plate. Thank you. Exactly. So those just screw in or nail, but we screw installed those directly over the ceiling joists. There's some particularities to the install, but they've got a great system. It's really quite straightforward. And then snap in your tubing and cover that over with drywall. And obviously the big issue there is if you're installing anything over any tubing ever, making sure you're not hitting the tubes with your fasteners is the big thing. And so some particulars there as well, but that was relatively straightforward to manage and design.
I was just thinking, I've done a lot of audits where I've seen radiant floors with the IR camera. Were you running warm water through and using an IR camera to decide where your screws were going?
That's a great question. We had layout marks on the drywall. Really helped in the places where that really mattered, and there was just good oversight and coordination with the drywall sub. So our crew installed the warm board. We had our drywall sub install the drywall, and it was just a well-coordinated effort. And we had our heating contractor install the tubing. And so we were able to spread this work over multiple subcontractors and effectively manage that without any incident. We were really thorough in quality control, and it's, again, like good planning, good communication, and good quality control, and you're good to go. But that is additional. It's definitely an additional complexity. And would certainly, would not shy away from that as being like a real, thing to manage, especially if you're not doing the work yourself.
Right.
And are subbing that out. You just need to know there's liability and it needs to get managed well there. Mm-hmm.
So,
but our experience. Oh, sorry,
go ahead. The question that comes to my mind next is comparable costs to another system.
Yeah, that's where I was going to go next. The warm board itself is not cheap, for sure. That was an expensive product. It saved a lot of install, and we actually were going back and forth as to whether we can do something ourselves, work with that product, see if there's something else that made more sense. It ended up working for us, particularly because we were installing that overhead, you know, on a slope ceiling going 20 feet up. Like, all right, we're going to go for ease of installation on this one because that, you know, the labor costs can get really high. This project was complicated, so I don't really feel like there were so many various factors, complexity of the shell, there's an interior timber frame, there's a, you know, multiple different zones in the system, so it's a little hard for me to like have some direct comparison to something else. Definitely more expensive than throwing up your garden variety baseboard, partially because of the cost of the warm board. In our case, not that that's the only solution. I've seen quite a number of more sort of do-it-yourself approaches or custom site build approaches. John Siegenthaler actually has some great examples of some radiant ceilings he's done. That's just layering up some polyiso board and putting up a grid to get your tubing to clip onto. And like, yeah, you could totally do that too. And I think that would probably comparable or lower costs than the warm board would be my expectation, depending on your labor and the complexity of the system. Compared to baseboard, I would say the baseboard is less expensive for sure. You're kind of the install, it's hard to beat, you know, having some long lengths of a thing that sort of mount and you clip the hydronics on one side. That's going to be a per BTU, like just by virtue of the material and installation. However, then you're looking at a thing, you have to like how that looks, you have to consider floor planning and you know, anything that's pushing up against that wall and all those issues that have plagued baseboard, you know, panel emitters for a really long time around. The couch blocks it, and then you get, you know, you lose 50% of your heat output, and the room is always chilly, and your couch is warming up, and like, all right, well, you factor that in over time in operating costs, and like, yeah, that's real. But yeah, no, this is not the cheapest way to deliver heat, but I would say it is the most comfortable and effective and lowest energy approach that I can imagine. I would do it in a heartbeat again. I was really, really happy with it. And we're actually looking at least one and potentially another project where radiant ceilings are definitely on the table for us.
I have been in a number of meetings on multifamily projects where I have said, you know what, you might want to consider a radiant ceiling because you can start off with a boiler, and then after the boiler kicks it in 15 years, you can, I mean, heat pump technology will be far advanced of what it is now. And we're talking with air to water COPs of, you know, 4, and we're probably going to be at 6 at some point in the not too near future. And I'm like, once you have the radiator in, you're good. And you know, you can have you done any cooling with it?
Yeah, so I don't know if we actually said this out loud, but it is an air to water system that's powering that building. And we are doing cooling. We are doing cooling in 2 of the bedrooms through a small fan coil system. So I am still not comfortable in residential construction where people like to open their windows in a hot, humid climate like Vermont, or at least during the cooling season, it's quite humid, running the risk of condensation and having cool surfaces.
Right.
I'm just not comfortable with that. I worry too much about condensation and associated mold risk. So we're not doing any chilled surfaces right now. If I could really guarantee that this was going to be in some sort of like static office building where I could really guarantee ambient temperature and humidity control to within a precise enough degree, then I'd feel a lot more comfortable around chilled surfaces. But what we do in this building is a separate cooling zone that when the system is in cooling mode, the heating zones lock out and it's just the cooling zone, and that runs a loop of chilled water to a fan coil that's in the basement, a ducted fan coil that then sends to some ductwork that branches and sends cooling service to 2 of the bedrooms. And we're looking at maybe expanding that to the rest of the house. And that's been a huge piece in mechanical design in our work in the last 5 years. It's gone from like, oh, if you have a high performance building and a relatively flexible client, then you really don't need cooling in Vermont. And that's really changed to,
You need cooling in Vermont.
You really need cooling. Like you got to plan that there are going to be periods of time where even like a high performance building with flexible clients are going to be like substantially uncomfortable for like extended periods of time in their home. And, you know, I don't think we're at the point of risk to, you know, survivability or like significant health impact on the cooling side as we have on the heating side, or as we see like, you know, in out west, and some of the, you know, the real health risk that comes from underserved cooling systems like they've been suffering for in the Pacific Northwest, where their infrastructure is also not designed for cooling loads and they've really been suffering. We're not there yet, but I absolutely expect that within my professional career, we will have some heat dome events that are going to result in significant injury or loss of life in our region as a result of lack of cooling infrastructure. So it's moving for me mentally from the point of luxury to the point of like actual necessity as we move into the next part of this century.
I think you're absolutely right. I am not designing, and actually have not designed any of my houses that I've helped design or been consulting on, leaving cooling out of the mix, just because it's getting warmer, and we're having these extreme events, and just because we haven't seen one here recently doesn't mean it's not going to come. And as the if you track, one of the things I like to track, I'm a weather geek. What can I say? I like to track the jet stream and how it looks. And the jet stream is looking like, you know, spaghetti, and it used to just look like this, you know, and that's causing a lot of these extreme events, and we're not going to be able to be designing houses. I am interested in seeing, and I could completely agree with you on the condensation risk of surface cooling. I'd like to see a robust monitoring system that ties into the radiant cooling and says, okay, if it is this humidity and this air temperature, then the maximum we can cool this water down to, and not with the safety factor and not get condensation, is this. And of course, when you're dealing with a radiant sealing system, you're not just worried about the condensation on the surface, but there are minuscule air gaps around your tubes, unless you've decided to mud the whole thing, which is one of the options to increase mass and things of that sort. But you could have condensation inside your wall and inside your ceiling.
Absolutely.
And that's
let alone all the distribution pipes that are going back to the unit, and whether or not those have really been insulated and sealed.
Exactly, yeah. Well,
and that's the thing to me.
No, go ahead.
I mean, that's what makes I get really nervous on our collective behalf as an industry, as we're like, oh, we need more cooling solutions now. Heat pumps are great. Heat pumps provide cooling services, and there's a jump in both the design and the implementation or sort of installation of these systems in terms of quality control for cooling that just isn't there with heating. Like, you have to worry about condensation issues on the heating side. On the cooling side, everything matters in terms of whether or not those pipes have been insulated and sealed or not. And I've heard dozens of cases of weird water stains in people's closets and random spots and funky mold situations because they didn't insulate and seal the cooling lines or the cooling ducts. I see that in ducted heat pumps where they just, the ducts haven't been insulated and sealed all the way up to the register, and you get condensation inside walls, and it breeds mold and creates really unhealthy situations. And like, that's really scary because I don't think that's on our radar. On the design side, designing for cooling loads is non-trivial. You really have to think about latent loads now. And there's this whole other host of inputs. You don't have to, there's no latent load on the heating side. So you do a UA, you add some infiltration, you leave a safety factor, and you're done. Not so with cooling, and solar gains are a really significant issue as well. So there's more siting and building form, window layout and orientation that like now mechanical design folks have to be thinking about. And then the other thing that really worries me is the turn down ratio on heat pumps.
How low can they go? What's the
for
minimum?
Cooling sides? Like, it's a problem. Like, if you're designing your heat pump system expecting it's going to provide both heating and cooling services, your cooling loads are 25% of your heating loads, and you only have like a 3-to-1 turn down on your heat pump, you're going to have some really inefficient cooling that is not going to do a good job of dehumidifying the air. And so you're going to have, and not going to, you do, like I see, like this is a problem. We have buildings with sort of damp, dank, kind of clammy air with a COP of not good because the
significantly below like the 3 it's
2 to 3 times the size of what the cooling load is because we just threw in one heat pump to do all the things. So getting back to the radiant ceiling air to water heat pump hydronic piece, the thing I get really excited about air to water hydronics is that, oh, there's now a hydronic system that can also provide cooling, which is freaking awesome for those of us in the hydronic world. It's like always the big thing. It's like, oh, it only does heating and paying all this money for this like amazing heating system and it doesn't do cooling. Air to water will do cooling. And if you've got this buffer tank of fluid, there is no turn down ratio issue. You can have a heat pump runs at its ultimate max efficiency. And then you have the super insulated tank with like negligible standby losses and the cooling load can just sip off of that as it needs to. And so from a design and efficiency, efficacy, exergy, and comfort standpoint, I'm like, that's it. Air to water with heat pump. And I like what you're saying around having some monitoring for some chilled surfaces. And then just be able to have some alternate control logic if the humidities inside the building are large.
Exactly. Yeah.
I think that's like the next, I think that's the next evolution as we've got, especially as we have smarter controls and better monitoring capabilities that don't cost thousands and thousands of dollars to get that information. And like, yeah, we could actually control for that.
We could actually have, surface temperature monitors and air monitors telling the thing, change the temperature you're sending and keep a safety margin of this. And that as the engineer, that's the first place I go. Let's try.
Yeah.
I think it's a beautiful system. I'm going to be installing it over at 10 Old Stage, which you have graciously enough come by a couple of times to take a look at. We'll be doing full install videos on that system and the choices that I've made. And of course, Jacob, I reserve the right to pick your brain about this into the future.
Pick away. I love talking about this stuff. It really is exciting. I'm not generally, as someone that does like all the mechanical either design kind of administration for new frameworks, even with that, I tend to not be a super techie kind of a person. It's not really my bag to like go straight to technology as a solution to a problem, but this is a pretty sweet piece of technology to have in our hands, the ability to do hydronic heating and cooling. And then as the sky's the limit on the distribution systems, but I'm psyched to see what you come up with for your ceiling design and help support as I can.
Well, I will certainly make sure that you're in on the loop on any questions that I have. And when we actually do the install, I'll have a couple of open days to have people, because everything that I do is an educational opportunity for someone, if not just for me, then for hopefully other builders who are saying, I think that's a horrible idea, and then come out and say, maybe this isn't such a bad thing. And if we can get a couple of companies making large volumes of the panels that can just click up and you can install them, then we can get the pricing down and get our HVAC techs used to this type of system. But I think I really like your fan coil cooling solution. That's a great way to protect you from the possible building durability issues and still be able to provide cooling with reasonable distribution losses. So I think that's a pretty cool solution as well. Of course, added cost. It'd be nice not to have to add the fan coils, but
exactly.
But what do you do?
Exactly.
You gotta provide a house to someone that they can actually use. We can't, make these things like the Starship Enterprise and expect normal people to be able to run it. We've got to make it something that is that most of the stuff is being dealt with passively, like you said. I recently was doing a design, and there was a large overheating issue. And the client, who's a designer, said, I found these great screens that you can clip into the window instead of a regular screen for keeping bugs out, and it reduces the
Mm-hmm.
solar gain by 87%.
Wow.
It's one of those kind of things that has a lot of little holes in it, so you can actually see through
Mm-hmm.
it, so you can see outside, but because
Mm-hmm.
it's outside of the window, and it's not something you have to put in and take out every time you want to use it, you just
Right.
leave it in place. It's got
Yep.
a very
Yep.
high ability to reduce the solar heat gain. So
That's huge.
also
That's great.
another interesting one last technology on the cooling side. There's a
Mm.
team at Carnegie Mellon that developed a new type of white paint. This white paint
Oh.
also reflects ultraviolet and infrared light. So the
Oh
surface
wow.
temperature of the paint is lower than the ambient temperature, even when full sunlight is on it. So
Wow.
yeah, who knows how long it's going to take before a gallon of that is available? But
Yeah.
imagine painting our houses with a paint that automatically cools itself. Um,
That's pretty
that's
incredible.
something that I'm really excited about too. Okay, well,
I love
I'm
it.
sure that we
That's the
could
one.
find another topic. I've had you sitting here for 2 hours. I appreciate the serial episodes that you're willing to go
It's
through.
fabulous.
I
Really
will
wonderful.
say thank you very much, Jacob Deva Racusin, for joining us here on House Calls Vermont. We'll have you back, and hopefully at some point also have Ace on. You're not the only person who speaks for New Frameworks,
Sorry.
but thank you again for taking so much time out of your busy schedule to chat with me. And I will check your crew social media to make sure they all liked and subscribed to the to House Calls
Love it.
Vermont.
Love it. Love it. Love it. That's great. Chris, thanks for the opportunity and thanks for all you're doing with keeping our industry moving forward on the right track.
You
Really
got it,
appreciate your
Jacob.
work.
Thank you very much, and say hi to everybody over at New Frameworks.
All right. All the best.
Okay, thanks.
Thanks. Bye.
Okay, that was it. I have this. I'm gonna now stop
Sweet.